Hello viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about propellant purity. So let's dive deep into it. So what do we mean by propellant? Well, propellant generally is a mix of oxidizer and fuel. Now let that be very clear. Oxidizer could be liquid oxygen, could be nitrous oxide, whatever have you. Fuel can be anything. It could be liquid methane or it could be kerosene, whatever have you. So package of those things are called propellant. You are not gonna call, oh, fuel is the propellant. No, both of them, package deal. And it must be very pure, and I mean ludicrously pure. Otherwise, bad things will happen, and we have learned it the hard way, so to say. So basically, what happens if you just know and you accept it? Like, the fuel is not as good as we want. This is what it is. Like, let's just say V2 era. You will have reduced specific impulse and thrust, and that is the primary reason why rockets from 1950s to 70s, they were really not that powerful, even though technically on paper they should be really, really powerful. It's just that the fuel was not that good, and fuel directly translates to rocket far more effectively compared to your road vehicle, because again, 1% impurities will have much bigger impact than you can think, much bigger. So we learned it the hard way that we must have very, very pure fuel. Another aspect is combustion instability, because you have to understand, if you have very clean, efficient burning, you will have powerful and efficient combustion. Good, awesome, done, go home. Combustion instability will be a hell of an issue for solving. For example, Saturn V F1 engines, they are very well known for combustion instability. But you have to understand, when you have that sort of problem, we have this engine that is going boom because of combustion instability. Everybody tried to solve it in their unique way. For example, the control command guidance guys, they're like, okay, we're gonna figure out some way to pulse the fuel so it can work effectively with that. So they were working on control algorithm, PID loops. Then you had people who are working on the engine, the mechanic people, they are like, no, what if we had baffles and all this? Okay. Then we have chemists, they're like, what could be the chemical cause of it? They're like, the fuel is not very refined. So they worked their ass off to refine the fuel to much higher grade, and all these things came together and this rocket worked. So we have learned it the hard way. Let that be very clear. It's not something that's like, it's not big of an issue. It's just like we learned it the hard way, is that combustion instability will become a hell of a hassle if you have that. And the primary reason for this is simply because of carbon buildup. And carbon buildup can cause some weird issue that you may not even think of. Like, for example, if you are running fuel around your rocket nozzle is hot and it has impurities, that impurity will become gel-like, or worst case scenario, it will literally create a clog there. And then you have clog, fuel will be choked, and voila, rocket goes kaboom. So we learned it the hard way. We have learned it very hard way that thou shall not have that. And injectors are very, very finicky. They need clean. So injector, all of those things. And for ICBMs, this is a weird kind of issue that learned the hard way and the long duration way, is that if you have hypergolics, which is not purely dry, like it has even some trace contaminants amounts of water, H2O into it, yeah, it will corrode the tanks. Don't ask how we learned that. So we have learned it the hard way. Let's just be very clear. We have learned it the hard way that thou shall use clean propellant. You cannot troll around in it, so to say. So let's start with the most popular one, LOX. Now, LOX is a rocket grade liquid oxygen. What does that mean? That simply means you are looking at 99.5% O2 purity. That's higher than medical grade. So that's pure. And then you have to understand how the heck we get oxygen. Well, there is generally only one way of getting oxygen. You take the air, you filter the hell out of it, you compress the hell out of it, and then you cool it, and then you expand it. The moment you expand a very highly compressed gas, it cools down. So in this scenario, we create a separation. Basically, it's exactly like how you have thermal-based crude oil thermal distillation. Same thing here, only the temperature is in negative. From our vantage point of, from Kelvin point of view, is exactly right. So the lowest point would be oxygen, second lowest would be argon, third would be nitrogen, generally by temperature. And then you collect this. Now here's the deal. You may think while we are going through this, there should not be any contamination in oxygen. While to some extent that is true, but not as much so. For example, the filtration process is not 100% perfect. While majority of particle contaminants can be stopped, gases contaminants, basically sulfur and NOx and things of that nature, not. So they will end up here, not in very large amount, but they will end up here. And then from here, it's still not that bad. But the moment you start to send it through piping, send it through pumps, send it through storage tank, storage truck, and then on-site, off-site, all of that, it slowly starts to build up a point where it's like, yeah, it's very contaminated. So we have learned it the hard way that we have to actually do quality control on this. So it's just not like, okay, we take oxygen, then do this. So you may be like, okay, why not SpaceX building this? Well, they want to build this. They want to build air distillation on site that will reduce the cost of oxygen procurement and NOx procurement by a lot. They just do not have the power on site yet. The moment they will figure out the power situation, 5 minutes later, this will start being constructed. It's like illogical to not have this. Like, still illogical to not have it right now, because they are paying for the same thing with some transportation costs and with their profit. So it's like, yeah, they're paying double the price for something that they need so much of. Unwise. So they're going to have that. And then you have to understand that once we have liquid oxygen, it has to be sent through this, basically what we call molecular sieves. Basically, these things have absorption characteristics that removes anything else. So you have liquid oxygen goes through, everything else gets filtered out. Even if you have small trace contaminants, majority of them will be, cleaned. And on top of that, because there is a serious risk of hydrocarbon contamination, because again, oils, pumps, all of those jazz things, it has to go through catalyst bed specifically designed for cryogenic temperature. Those beds oxidizes hydrocarbons. When you do that, that's far safer rather than having unburnt hydrocarbon in a place where you are running basically oxygen contaminated with hydrocarbon as a cooling jacket. Yeah, that's a boom event waiting to happen. So we learned it the hard way that we must use catalyst beds to remove any hydrocarbons. And after that, we do continuous quality monitoring. Basically, if there is a giant pipe, there will be a smaller pipe that will go and it will expand all the gases, and that gas will go through a whole plethora of sensors, laser sensors, and mass spectrometers, and this and that, all sort of sensors which can detect even the tiniest impurities, basically ppms to bpms, billion parts per million, parts per billion, so to say, like ppb. So bonkers amount of resolution has to be spent so you can have very high confidence that the product is good for rocket. And then we put this puppy into rocket and just launch it. So this is LOX. So it's not just, oh, liquid oxygen. Yeah, it's like, unless you have it on site, then you can control it. But other than that, it's like, nope. Then we come to RP1, this puppy. To this day, I do not understand how the heck it looks like this, but it is what it is. RP1 is basically you take kerosene and you ultra refine it. So that's rocket propellant 1. Basically the answer from Saturn V. And it's a multi-stage process. It's not just like we take kerosene, we filter it, done, go home. So we start with clean, high paraffin crude oil. Basically same way when you're looking at coal, not all coals are same. Some coal have very high carbon content, some have very poor carbon content. Same way with crude oil. Some places crude oil is like GG, smooth. Some places is like so we have to find good source, basically high paraffin. Once you have that, that's a clean starting point. Once you go there, then you do hydro treating, so to say, or hydrogen hydroid sulfurization. Basically, you put too much hydrogen into it, mix with it, and then you send it through nickel molybdenum catalyst. That allows them to basically leach all the sulfur, because sulfur is a bad puppy when it comes to hydrocarbon. Really, really bad puppy. So it removes sulfur, it removes olefins, it removes aromatics. Basically, it's chemically just removing all the naughty puppies. They're just like, let's just, you do not need to be in the fuel pipeline. You just need to let it go. Just let it go. And then we send it through filters. And the reason we are sending it through filters is because it does have a lot of dissolved gases. And you're like, why? Well, you have tank has pressurization, so things do dissolve. That's the reason why jet fuel generally has to have some things that make sure that it does not freeze. Why? It's like, it's not unclean. No, when you go up and you're expanding, creating void space in your fuel tank, atmospheric air comes in, moisture condenses, tada, water contamination. So we have learned it the hard way that you have to figure out a way to remove dissolved things, basically CO2 and O2. So all of that, but again, that's not that difficult. This hydro treating is the really expensive part. Second expensive is the finding a good source. Then you can do that, and be mindful, there are many more steps, but these are the bulk process. And then you do high quality control, same way, like you actually sample it, actually test it, and if it's not pure enough, there's a problem, because this is designed in such a way that when it's going around the rocket engine, it will not catch on fire, it will not try to decompose. In the lack of oxygen, it does not mean there won't be a reaction, because it's a long hydrocarbon chain. It can react, basically break apart into smaller things, or worst case scenario, fold up into a larger block, will make a coke. Basically, it will first go from liquid to gel to blah. So once it reaches that, your engine is clogged. We have learned it the hard way. So that's why it has to be very pure. So it will take serious amount of horsepower to catch this puppy on fire. It's not easy to catch on fire. So again, purity allows it to happen. And again, F1, without this, F1 was not possible. So this, and again, this is the sole reason Elon Musk is big. Falcon 9. And again, that's why this is because of this purity. Igniting this puppy is so hard that they're like, yeah, just throw another chemical into it. It's much easier. Electrical spark ignition of these puppies are difficult as hell, like difficult. So that is RP1. Then we come to CH4. The RP1 is the fuel of yesterday. Fuel of tomorrow is CH4. Now, liquid methane comes from LNG. So, same way oxygen comes from air, liquid methane is generally extracted from LNG, these puppies, so to say. Now, be mindful, these puppies do have certain criteria to meet, otherwise countries will not buy it. I'm not gonna buy from Russia if they're like, hey, our quote-unquote methane carrier does not have enough methane. So, generally the minimum cutoff point is 85% to 95%. So, when they are sampling this, again, they will do sampling of this when they are unloading it, so to say. And if it's 80 to 95, then there will be lawyers involved, so to say. So 85% to 95% should be pure methane, CH4. And then you have ethane contamination, propane, butane, and those things are not big of an issue if you are just using this as a combustion fuel for, let's say, trucks. A lot of truck companies are trying to use LNG as a fuel. We can do that. Cool, awesome, no problem. You can expand this and make it into CNG, compressed natural gas. A lot of Indian states already have that infrastructure. No problem. Like ethane, propane, butane is like, nah, who cares? But there are some other things that does cause some mess, so to say. We have nitrogen, we have trace of carbon dioxide and sulfur. For some reason, sulfur is everywhere. So, and water vapor is also there, which you would be shocked. How the heck water vapor comes here? It's just that, yeah, contamination. It's minor contamination, slow by slow, it does pile up. So we send it through cryogenic fractional distillation, exactly the same thing we do with air, and that allows us to remove almost 3 to 4 major components. Basically, nitrogen yeeted out of there, ethane yeeted out of there, propane yeeted out of there, and some other gases if they are contaminated. Generally, this is the place where they go from 85% efficiency to almost 99% methane. But after that, you still have contamination. Basically, contamination would be measured in ppms or ppb. So in those sort of scenarios, we send it through absorption, polishing, and you will keep hearing this word, infiltration, polishing. Polishing simply means you removing those very naughty particles. So in those sort of, again, it's sent through a molecular sieve to remove sulfur compounds and trace hydrocarbons. I'm reasonably sure I do not need to explain why having hydrocarbon in a liquid methane scenario going around a very hot thing is not wise. So, and again, the benefit of this, your rocket is not like Falcon 9. Falcon 9 goes up white, comes back black. This is like, I'm going up shiny, I'm coming back shiny. Thou shall not change my shininess. It's shiny fuel. Again, the long hydrocarbon chain production is almost negligible. Like, nope. So those are the good part of CH4. So what can we look into the future? Basically, what is the future holds? Yeah, everybody is working their ass off to reduce cost. That's the whole point. Basically, rockets went from like once in a while to like, no, every one rocket per day is the target of humanity right now. So we want to reduce cost. So basically, that was not an issue. Back in the day, fuel purity or propellant purity was not an issue because your rocket was so goddamn expensive. So basically, if SLS says, I'm gonna take over $2 billion to launch SLS once, and the fuel cost is like, even let's say $5 million, it's like $5 million is billion missing. It's like 2 billion missing, so nobody cared about it. But as we are making rocket reusable and we are trying to make rocket cheaper, yeah, now the fuel, because again, there is an inherent cap how cheap you can make a rocket. There is an inherent cap. So once you reach that point, and people can easily project how low that they can go, they look into other things. How can we improve that? Like, second would be increasing cadence. Okay, let's say you reached a maximum cadence that you can practically do. What else? Fuel. The propellant is too goddamn expensive. So as we are reaching a point where reusable rockets are becoming a thing and everybody is working on a reusable rocket, the fuel cost is becoming much larger concern rather than how it used to be in the past. In the past, nobody cared. It's like, if you need to create a whole rocket, defense sector fuel plant to just make, let's say, jet propellant 10 that is used in cruise missiles, you could do that because again, rocket was so goddamn expensive. Nobody cared about this. Now that is not so much. So removing SpaceX is working on Raptor, and Raptor is too goddamn hot, meaning if metal is melting here, Raptor is pushed here. It's almost there. Pressures are too goddamn high, temperatures are too goddamn high, and like they're just pushing it too hard, like going into it. So penalty is they cannot risk. If they are pushing your engine that badly, you have to make sure the fuel is like GG clean. So they cannot deviate from that. However, every other company is working their ass off to let go of this pure propellant scenario, so to say. For example, ISRO is switching from RP1, which was ludicrously expensive, to ATF. ATF is aviation turbine fuel. And then you have Blue Origin. They are going into LNG. And they still have like some filtration, but it's much simpler compared to like the whole process. And other companies are directly taking LNG. Like LNG coming from the tank, we are putting LNG into this. Now you're like, okay, how the heck they can work? Well, still our computers are much better, and B, we are planning for those things. We are planning from day one, and C, our material technology is good enough where we can make rockets light enough where the penalty of these sort of things are not that big of a deal. So if you design your rocket from day one, hey, you only gonna receive LNG, which again, let's say should not be below 85%. At that point, it's a reject batch. So 85%, you will program your computer based on that. It's like, what's the worst contaminated fuel I can receive? Okay, 85%. What happens with that? Okay, your specific impulse will go down that. You plan for that. So basically, computer is always full throttle, going as high up. So like, whoa, 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 I'm getting too much power, because again, fuel is not contaminated. So like, okay, throttle down. Throttling down is much easier. And almost all companies are not making engines going blow hard like Raptor. Raptor is too hard. It's like, but every other company is like, hey, bro, chill. It's a reusable system. Chill. So every Tom, Dick, and I look into Relativity Space, Firefly, Blue Origin, and other companies are also. So almost everybody is trying to reduce the fuel cost, because again, once you have a reusable rocket, there will be upper limit how cheap you can make it. At that point in time, even 10% savings of propellants would be huge. And be mindful, it would be much more than 10%, specifically if your LOX and basically CNG does not need to be purified a lot, like LNG, sorry. So this is a good development, better material science, better computer dynamics, better understanding of all the things. We are reaching a point where it's like we no longer have to worry about those things, especially if they are designed like that from day one. You can't do that with Raptor. Raptor will go kaboom. So this was my presentation on propellant purity. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.